Chapter 1 Vectors. Learning Objectives. By the end of this chapter, you should be able to understand what a vector is, distinguish between scalar and vector quantities, represent vector using coordinates, add and subtract vectors, multiply a vector by a scalar, compute the magnitude norm of a vector, interpret vector in a physical situation. Why do physicists study vectors? Before we learn to manipulate vectors, let's answer an important question. Why are vectors so important in physics? The answer is simple. Physics describes nature, and nature exists in space. Whenever we study motion, forces, electric fields, magnetic fields, momentum, or even quantum mechanics, direction matters. For example, Newton's second law is written as F equal to mass multiplied with acceleration. Notice that both the force and the acceleration are vectors. Without vectors, Newton's law could not accurately describe motion. Vectors are one of the most fundamental mathematical tools used throughout physics. Scalar and vectors. Before defining a vector, we need to distinguish two different kinds of physical quantities. Scalar. A scalar is completely described by a single numerical value. Examples include mass, temperature, time, energy, electric charge, pressure. For example, the temperature is 22 Celsius degree. No direction is needed. A single number is enough. Vectors. A vector requires more information, as a vector has magnitude, direction, orientation, or sense. Examples include force, velocity, acceleration, displacement, momentum, electric field, magnetic field. Suppose someone tells you, my car is moving at 100 km per hour. Is it enough information? No, you still don't know where the car is going. Speed is a scalar, velocity is a vector. Graphical representation. Vectors are usually represented as arrows. Every vector has a starting point, origin, an end point, a direction, an orientation, a magnitude. The arrow points toward the vector. The arrow points toward the direction of the vector. The longer the arrow, the larger its magnitude. Vector coordinates. Although arrows help us to visualize vectors, computers and mathematicians prefer coordinates. In two-dimensional space, a vector is written as u equal to x and y. For example, u equal to 3 and 2 means 3 exists along the x-axis, 2 units along the y-axis. Three-dimensional vectors. Most physical problems occur in the three-dimensional space. A vector becomes u, x, y, and z. The third coordinate represents the displacement along the z-axis. Vector addition. Adding vector is straightforward. We simply add the corresponding components. Example, u equal to 2 and 5 and v equal to 4 and minus 1. Adding them gives u plus v equal to 6 and 4. Each coordinate is added independently. Scalar multiplication. Suppose we multiply a vector by a number. If u equal to 3 minus 2, then 2 multiplied with u equal to 6 and minus 4. Every coordinate is multiplied by the scalar. If the scalar is negative, the vector reverses its orientation. Linear combination. One of the central ideas of linear algebra is a linear combination. A linear combination is written as w equal to a multiplied with u plus b multiplied with v, where a and b are real numbers. Almost every topic in linear algebra, from vector spaces to quantum mechanics, build upon the simplest concept. Magnitude norm. Magnitude of vector tells us its length. For a vector u equal to x and y, its magnitude is norm of u equal to square x power 2 plus y power 2. Example, u equal to 3 and 4, then norm of u is scalar 3 power 2 plus 4 power 2 equal to 5. This is simply the pure Pythagorean theorem. Physical application. Vectors appear everywhere in science, mechanics, force, velocity, acceleration, momentum, electromagnetism, electric field, magnetic field, fluid mechanics, fluid velocity, computer graphics, position, rotation, animation, robotics, motion of robotic arms, artificial intelligence, feature vectors, image representation, natural learning language, language processing. Chapter summary. In this chapter, we learn what vectors are, how they differ from scalar, how to represent vector, how to add vector, how to multiply vectors by scalar, how to compute their magnitude, their concept by the foundation of linear algebra. Exercise. Exercise 1. Classify each quantity as either a scalar or a vector. Temperature, force, pressure, energy, acceleration, mass, and electric field. The solution. Scalars are temperature, pressure, energy, and mass. Vectors are force, velocity, acceleration, electric field. Exercise 2. Describe the vector u equal to 5 and minus 2. Solution. Vector moves 5 units to the right, 2 units downward. Notice that a negative y coordinate means movement downward. Exercise 3. Compute 2 and the vector 2 and 4 plus 5 and minus 3. Solution. First component 2 plus 5 equal to 7. Second component 4 plus minus 3 equal to 1. Therefore, the scalar is 7 and 1. Exercise 4. Compute the scalar minus 3 with the vector 2 and minus 4. Multiply each component by minus 3. First component minus 3 multiplied with 2 equal to minus 6. Second component minus 3 multiplied with minus 4 is equal to 12. Therefore, the vector is minus 6 and 12. Find the magnitude of u equal to 8 and 6. Using the norm formula, norm of u is square of 8 power 2 plus 6 power 2. Then it's square 64 plus 36 equal to scalar 100 is equal to 10. The vector has a magnitude of 10 units. Exercise 6. A drone flies 10 meters east, then 24 meters north. Write the displacement vector. Compute its magnitude. The displacement of vector is 10 and 24. Its magnitude is scalar square of 10 power 2 plus 24 power 2. It goes square 100 plus 566 equal to square 666 equal to 26. Therefore, the drone is 26 meters away from the starting point. Notice that the total distance traveled is 10 plus 24 equal 34 meters, while the displacement is only 26 meters. The distinction is extremely important in physics. Exercise 7. Under 3 forces act on an object. Force 1, 4 and 1. Force 2, minus 2 and 5. Force 3, 3 and minus 4. Find the resultant force. Solution. Add the x components. 4 minus 2 plus 3 equal to 5. Add the y component. 1 plus 5 minus 4 equal to 2. The resultant force is R equal to 5 and 2. Its magnitude is norm of R is square of 5 power 2 plus 2 power 2 equal to 29, equivalent to 5.39. This is the single force that produced the same overall effect as the 3 original force combined. Common mistakes. Many students make the same mistakes when learning vectors. Avoid this common error. Confusing a point with vector, forgetting that vectors are both direction and orientation, adding magnitude instead of components, forgetting to square each component when computing the norm, confusing distance travel with displacement. Final thoughts. Vectors are the foundation of linear algebra and one of the most important mathematical tools in physics. Every topic that follows vector spaces, matrices, linear transformation, eigenvalues, eigenvectors, and quantum mechanics builds upon the concept introduced in this chapter. Take the time to master these fundamentals. Once vectors become intuitive, intuitive, the rest of linear algebra become much easier to understand.